For this question, you just got to know what hydrogen bonding structures are necessary. In order for something to do hydrogen bonding, it doesn't just have to have hydrogen. It has to have hydrogen specifically connected to nitrogen, oxygen, or fluorine. There are hydrogens all up in molecules 2 and 3, but they just don't have the right bonds. And just because something has nitrogen in it, or oxygen in it, or fluorine in it, does not mean it can do hydrogen bonding. There specifically must be a direct connection between the hydrogen and the nitrogen, the oxygen, or the fluorine. And there's only one thing that has that. That's why it's only the first one. This one says, which of the following statements explains the trends observed in the following chart? So we are seeing here that we have boiling point, and notice how water has like a super high boiling point for its size. It's kind of unusual. That's because it can do hydrogen bonding in two different locations. It can do hydrogen bonding on the left hydrogen and hydrogen bonding on the right hydrogen. So there's a bunch of things that this says. So in this particular case, it's probably easier to go through the answers when you're taking the test and kind of think about it logically. So this first one says the molecules H2S, HCl, and pH3 have the lowest boiling points within their respective groups because of their high polarity. Well, that doesn't really make sense because high polarity would mean a high boiling point, so that doesn't make sense even just logically. The next one says boiling point rises with molar mass. That's true. Heavier things tend to have higher boiling points. But the first member of each group shows abnormally higher boiling points due to hydrogen bonding. So the molar masses are increasing as you go toward the right because they're getting heavier. Huh. That does not look right. That was actually the right answer right here. The boiling points rise with molar mass, but the first member of each group shows abnormally higher boiling points due to hydrogen bonding. H2O can hydrogen bond because remember it has a H directly connected to an O. HF can hydrogen bond. NH3 can hydrogen bond. They have higher boiling points because they can hydrogen bond. So this is actually, I believe, to be the right answer. It is not true that the only intermolecular forces exhibited by the molecules are London dispersion forces. That's just objectively not true. So it must be a mistake there. London dispersion forces are the only forces exhibited by molecules if they are nonpolar. Basically, that's just the answer. If they're nonpolar and don't have any hydrogen bonding capabilities. So I would say this is the right answer. All right. 18. Which of the following substances are dispersion forces? Which of the following substances are dispersion forces the only type of forces present? That basically means you're looking for something that's non-polar. So anything that has, and again, you might have to sketch these out. Anything that's ionic, strike it. Anything that's polar, strike it. And anything that can do hydrogen bonding, also strike it. So this is a good example of when you have to go through piece by piece, and the reason that this is the right answer is because I2 is nonpolar. CCl4 is also nonpolar because it's a carbon surrounded by 4 identical atoms. NAF is ionic, so that would not count as only having dispersion forces. HBr is polar, so that also wouldn't count. PF3 is polar. If you were to draw it, you'd see a lone pair on that central atom. So basically, we have a whole bunch of polar stuff, whatever. The only reason that this is the right answer is because I2 and CCl4 are nonpolar. Recognize that anything that's diatomic is nonpolar. So I'd be like H2, O2, I2, Cl2, F2, N2. All those things are nonpolar. So if you get to the test and you're like, is this polar or not? Diatomic things are nonpolar. Also, if you see a carbon surrounded by either a bunch of hydrogens, like, CH3CH2CH2CH3. If you see only carbons and hydrogens, nonpolar. Another trick is if you see carbon surrounded only by the same atoms, for example, CF4 or CCl4 or CBr4, those are also nonpolar. So there's a lot of ways they can come in. Just recognize what's polar or nonpolar off the bat. 19. Rationalize the difference in boiling points between CH2BrCl and CH3Br. So this has a much higher boiling point. Whoops. CH2BrCl looks like this. So you have a carbon in the middle. You have 2 hydrogens. You have a bromine somewhere, and then you have a chlorine somewhere. This is polar. But so is CH3Br. So let me duplicate this. Okay, move this around. So there's one of our molecules. Here's the other molecule. Obviously, the only difference is I'm going to replace the Cl with H. So we have two molecules that are polar. One clearly has to be more polar. And the reason is it's more polarizable because it has a higher molar mass. So if you have two things that are polar and you're like, which one's going to have a higher boiling point, or why does one of them have a higher boiling point? They're both polar. Neither of them can do molar mass. That comes back down to London dispersion forces, effectively. Something that has more electrons and has more mass in general is going to be more polarizable. It's just going to be harder to turn into a gas. That's why it has a higher boiling point. So think about mass when everything else fails. Select or predict the strength of the intermolecular forces from strongest to weakest. Now, again, weakest is going to be something that's going to be nonpolar. So you're looking for your nonpolar thing on the very right. And as I said earlier, we know that hydrogen and any other diatomic thing is going to be nonpolar. Pure hydrogen, pure nitrogen, pure oxygen, anything that's like H2, O2, F2, Cl2, Br2, those are nonpolar. But then you're looking at the other ones, you're like, well, what then? The reason that this can be a little bit tricky is because you're looking at two things that are very clearly polar. Both of these are polar. So as you may remember from, I think, Gen Chem, the first part of Chem, there are electronegativity values for every thing. And also, you just remember in general, you definitely need to remember your periodic trends. Fluorine is the most electronegative element. It has an electronegativity of about 4.1 on the 4.0 on the Pauling scale, or whatever it's called. Then you have chlorine, bromine, and iodine. So if you're looking at this middle part, you're like, well, I know HF is polar and I know HCl is polar. HCl is less polar than HF because fluorine has electronegativity of 4.0. I think chlorine is 3.5, and I believe hydrogen is 2.0. So if you look at HF versus HCl, and I'm getting these numbers off the top of my head, I believe that hydrogen is like a 2.1 or 2. Whatever. It doesn't matter because it's the same. Let's call it a 2.0. And then fluorine's a 4.0. And over here you have hydrogen, which is like a 2.0 or something like that, versus chlorine, which is like a 3.5. The chlorine is less, there's less of a difference between H and Cl's electronegativity, so HCl is less polar. So you have something that's non-polar, something that's less polar but polar. HF is more polar, and when you get to such an extreme where, remember those electronegativity values, Na and F are so different that they're ionic, and that's going to be the strongest one, so that's why that's the answer. Based on this table, which of the following compounds should have the lowest boiling point? So something that's going to have the lowest boiling point when it has, the lowest boiling point, and when it has the, okay, so wait, hold on. This is another one that's a little bit weird because acetonitrile has the greatest dipole moment, which basically means it's the most polar. And when something has a high polarity, you could think of it as like the molecule being very sticky, so it's going to have a high boiling point. So a high dipole moment, the greater the dipole moment, the greater the boiling point. So let's like write that down. A higher dipole moment equals a higher boiling point. So the dipole moment for acetonitrile is the highest. It should actually have the highest boiling point. And then the dipole moment for dimethyl ether is lowest. It should have the lowest boiling point. So if this says the lowest boiling point, the answer should not be acetonitrile, I believe. I would double check with your professor, but maybe that's like a typo mistake thing. 22. Which kind of hybrid orbitals does the central atom use in CH2O? This is a lot. Not this question being a lot, but in terms of, I just happen to remember this really well from organic chem, so I'm going to try to put myself in the perspective of a Gen Chem student again, assuming you learned it the same way. So first of all, if I were to draw out appropriately, which looks like formaldehyde or don't remember exactly what it is. It's not important. But if I were to, I'm going to actually make it bigger. So you have C in the middle, and you have two two bonds that make a double bond with the oxygen, and then you have a hydrogen and hydrogen. I think this is formaldehyde. I don't know. But what you have to recognize is that every single bond is a sigma bond. And again, I don't specifically remember if you learned sigma and pi, but I'm believing you did. And then every double bond has one sigma and one pi. So when it comes to hybridization, you have sp, sp2, sp3, and these have direct links to shape. So the easiest way that I tend to think about it is this. This central atom here, this carbon, has a trigonal planar shape. So this entire molecule has a trigonal planar, so flat triangle geometry. Trigonal planar geometry is going to correspond to sp2. So you can think about this as sp2, so it's like sp2 with like a pure p orbital, which is basically kind of like what's going to come from this. So they're going to hybridize, and the easiest way that I remember this is that trigonal planar or flat triangles are going to be sp2. Pick a color. This would be sp2. So here's a summary for how I think of it. If something is linear, let's say you have carbon dioxide. So you have carbon dioxide, so it's a linear molecule. So this is linear. That's going to be sp. You can think of it as like two hidden pure p's, which are going to be like the pi's, right? So if you zoom in on here, you have like a pi and a pi. Those are going to be like these two things. And then you have your sigmas, which are going to be hybridized into p. This is the terrible explanation, but I'm showing you how to get through this quickly in terms of how to think about it. So if something is linear, sp, because it's going to have two pi lines, which are basically two p's removed from it. So the maximum that you got to, it's going to have two p's removed from it. So this is just like a super fast, not technical summary. If something is not linear, so actually in this case it's like trigonal planar, it's going to be sp2. Notice how you have a pi that's kind of like out here by itself. That's the missing p. And then lastly, if you have something that is tetrahedral, so you have carbon, and then you have like a hydrogen, 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 hydrogen. Notice how you have all sigmas. This would be a sigma, 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 sigma. So you're going to have just sp3. So super fast, not technical summary. You have sp, sp2, and sp3 for the basic hybridizations, and that's going to correspond to a linear geometry, a trigonal planar geometry, and a tetrahedral geometry. And that's like the super fast crash course. You can't teach a whole section on hybridization in 4 minutes for this one question that I'm trying to explain to you now, but it's not too bad if you want to just learn how it works quickly. And that's why it's sp2, because it's trigonal planar, or that correlation is there. A molecule has two lone pair and two bonded atoms on the central atom. What is the hybridization? Again, comes right back to Vesper theory, sort of. So imagine you have some central atom. Let's just call it A. It has two lone pair, and it has two bonded atoms. Let's call those X. This goes right back to what we said. Oh, by the way, this is related to electron region geometry, so that's going to help us with 23. So remember that for electron region geometry, it's how many things are around that central atom. There's 1, 2, 3, 4 pairs of electrons around that central atom. 2 are lone pair, so you have a lone pair. Whoops, that's a 4. We have a lone pair here. We have another lone pair. And then we also have 2 bonding areas. Bonding area, bonding area. It doesn't even matter that you have 2 bonding areas and you have 2 lone pair, because collectively this is still 4 electron regions. And if there are 4 electron regions, the hybridization is sp3. If there are 3 electron regions, then the hybridization is sp2. And if there are 2 electron regions, the hybridization is sp. Just like what I said up here, where you have linear, that's uh, 2 electron regions, so 2 ER. And then trigonal planar is 3 electron regions. And then tetrahedral is 4 electron regions. Another trick, and this is like, again, super like not technical, add up the superscripts. Because 1 plus 1 is 2 electron regions. 1 plus 2 is 3 electron regions. And then 1 plus 3 is 4 electron regions. So if there are 2 lone pair and 2 bonded areas, or bonded atoms, and there's 4 electron regions. And that's why the superscripts here add up to 4. 1, 2, 3, 4. That's like a super fast way to think about it. Ooh, got a little blurry. Okay. This molecule has how many sigma and pi bonds? Well, we just talked about this. Sigma bonds are going to be every single bond. So let's go through and do all the sigma bonds. So we have a sigma, 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 sigma. So we found all the singles. Remember that every double also has a sigma bond. So let's see, we have 1, 2, 3, I forgot one over here, 4, 5, 6, 7, 8, 9, 10, 11. So far we have 11 sigma bonds from all the singles. But don't forget that double bonds also have a sigma. We have one here, one here, one here. So I'm adding another 3 sigma. And then one here. I'm just keeping track. So I added another one. So currently we have 4. Hold on, I can't do math today. 15. So if I clean this up and write my final tally, there are 15 sigma bonds. Sigma bonds are going to be found, they're the only type for single bonds. So all those are sigma. But don't forget that pi bonds are the other line in a double bond. I'll do those in orange. That's a pi bond. That's a pi bond. That's a pi bond. And that's a pi bond. So we have 1, 2, 3, 4. And that's our answer. 15 sigma and 4 pi. Now, what if there were a triple bond? Suppose you had something that looked like this. Triple bonds work this way. Triple bonds are going to be made of a single sigma and then 2 pi's. So that's a pi, and then that's a sigma, just in case you see it. Which hybrid orbitals overlap between C1 and O1 in the following species to form the CO bond? So it's going to take, so I guess thinking about it with the trick I showed you earlier, that C has how many electron regions around it? Well, it's going to have 1, 2, 3. So there are 3 electron regions. Now the geometry around that happens to also be trigonal planar. That's the electron region geometry. As we said earlier, that means it's going to be sp2. So we have sp2, sp2, sp2. sp would be linear and sp3 would be tetrahedral. So those are not in the running anymore. Now you're like, okay, well that's around the carbon. What about around that oxygen? So here's the oxygen, the O1. This oxygen has hidden lone pairs. I think it's a little bit tricky, but remember, this oxygen is going to have 2 lone pair that are not going to be shown. All these oxygens are going to have 2 lone pair. Except for this one on the end, which is going to have 3 lone pair and a little negative. But that's not even in here. So it looks like an amino acid? I don't know. All right, so sp2 is the hybridization around the C1 because it's trigonal planar. But around this oxygen, we have how many electron regions? Let's count them up. This oxygen has 1, 2, 3, 4 electron regions. So 4 ER. Now 4 ER means it's going to be sp3. So again, really get the difference between sp1, sp2, sp3 in terms of their geometries, and that really is the easiest way that I can think about it for here. So that's going to be tetrahedral electron region geometry. And that's why this is your answer here. To think of it another way, the trigonal planar geometry around that carbon is why it's sp2, and the tetrahedral geometry around that oxygen is why it's sp3, and that's the overlap. NH3 reacts with BF3 to form a new addition, well, to form the new addition compound H3NBF3. Which of the following illustrations best depicts the change, if any, in the orbital hybridization of nitrogen in the reaction? So nitrogen is going to have, see, so like let's just draw out what it looks like at first because it's probably easier to look at it from a molecular standpoint. So NH3 looks like this. I'm going to put the lone pair on the right. H, H, H. And then you have BF3, which has, I believe, an untapped pi orbital, and then the 3 fluorines around it. Okay, yep. So let's talk about what the hybridization is going on around this nitrogen. This nitrogen has 4 electron regions right now. Those because it has a lone pair and then 3 bonding areas, which means that it's going to be sp3 hybridized, otherwise known as a tetrahedral electron region geometry. Now, if you're thinking back to Gen Chem, like the first part of Gen Chem, you're like, well, didn't y'all say that NH3 is trigonopyramidal? That's the molecular geometry. We don't care about that right now. We care about the electron region geometry, which is how many things are around it? 4. You got bonding area, bonding area, bonding area, lone pair. That's 4 electron regions, which correspond directly to sp3. Which means that all of these are going to be sp3. So I'm going to highlight sp3 in yellow. sp3, 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 sp3. All those are sp3. Now the question becomes, well, does it remain sp3 hybridization? Does it keep the same molecular geometry once these lone pair link up with the open p orbital in the BF3? So let's see how that works. Let's get rid of this. And now we're basically like drawing it this way. So I'll do it purple. Then we're going to add on this. So we added on a line connecting the BF3. And we're going to ask ourselves, well, now what's going on around this nitrogen now? It turns out that this nitrogen still has 1, 2, 3, 4 things around it. It still has an electron region geometry. It still has 4 electron regions, which means that the hybridization has not changed. It's still sp3. So it started as sp3 and it remained sp3. And that's why figure B makes sense. It did not gain any, it did not become more hybridized in terms of like adding another orbital in there or anything like that. It just used the open p orbital and put 2 electrons in it. Those 2 lone pair electrons. Consider the following molecule. What type of hybrid orbital do the lone pair of In what type of hybrid orbital do the lone pairs of s reside? So S is right here. And again, I can't stress this enough. If you know your electron region geometries, then you got it. So let's, again, remind yourself. There's linear. There's, and I'm only going to do the main ones. There's linear. There's trigonal, planar, and there's tetrahedral. So linear is going to be 2 electron regions. Trigonal planar is going to be 3 electron regions. And then tetrahedral electron region geometry is going to be 4 electron regions. So electron regions, remember, are just anything, whether it's a lone pair or a bond, that is around that atom. So we have a sulfur here. How many things are around it? You have a bond, so that's 1. A lone pair and a lone pair, that's 2, 3. And then another bond, that's 4. There are 4 things. That's a tetrahedral electron region geometry, which you just need to know corresponds to sp3. Take away, every time you add a pi orbital, you take away one of those p's. So if this were a double bond somewhere, it'd be sp2, and then linear is just sp. So this is sp3 because it's a tetrahedral electron region geometry. That's the connection that you need to see. This is very key, as you see from some problems beforehand. According to valence bond theory, the triple bond in ethyne is composed of, and I said it earlier, it's just one of those things you got to know. You just got to recognize that whenever you have a triple bond, it's a sigma and 2 pi. By the way, whenever you have a double bond, it's just a sigma and a pi. And if you have a single bond, it's just a sigma. So it's just kind of know those. Pretty simple. 29. How many sigma and pi bonds respectively are there in this molecule? So this is one of those ones where you kind of have to just draw it out, and hopefully you had some practice with learning how to do these. So let's do it. You have a carbon with 3 hydrogens on it. That's going to be the end cap. H, H, H. Then you have the next carbon. So my recommendation is find all the carbons first. So you can actually put all the carbons in a row. There are 5 carbons, so let's put the 5 carbons out like this. We took care of the first carbon, and it's 3 hydrogens. So that's all right here. Next carbon has 2 hydrogens on it, so we can put those up and down. Of course, we want to link all of our carbons at least once. You can do that now. Now the third carbon, I guess I can call this carbon 1, carbon 2, carbon 3, carbon 4, carbon 5. So 1, 2, 3, 4, 5. The third carbon has just 1 hydrogen on it. Doesn't matter whether you put it up or down, but it has just 1 hydrogen. The fourth carbon also has just 1 hydrogen. And the third carbon is another end cap carbon, which typically, not always, is going to have 3 hydrogens. So if it helps, kind of like trace these out and like see like, okay, those are those, and this is that one, and then this is that one, and then this carbon with its 2 hydrogens is this one, and then this end cap carbon with its 3 hydrogens is that one. So all those colors hopefully kind of make some sense. Now you're remembering, carbon needs to have 4 bonds. So the third carbon only has 3. That means we have to have the double bond somewhere. We cannot put the double bond on the left because that would create 5 bonds with the second carbon. We got to put the double bond here between carbons 3 and 4. And that actually satisfies the deficiency in bonds that carbons 3 and 4 had. And now they all have 4. Then you go through and you label your sigmas and your pi's. Sigmas are going to be green. Every single bond is a sigma bond, so don't forget. So we have 1, 2, all those many. I'll count them up later. So we have all those sigma bonds from the singles. And then we have that one double bond. Remember that double bonds also have a sigma. But the other line in a double bond is not a sigma. It's a pi. So if you count them all up, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 sigma bonds. That's why that's the answer. But we only have 1 pi bond. And that one, I don't know why I drew a pi there. This would be there we go. Good thing color coding is there. So that other line in the double bond, that's a pi. So remember, double bonds are made of a sigma and a pi. What kind of hybrid orbitals does the central atom use in BrO3? So that's the bromate ion. So if you were to draw out using the Lewis structure stuff, let's see, bromine is 7, and then there's 3. So I'm counting out the number of valence. So 7 from bromine, and then each oxygen has 6, and then we add 1 because of this negative charge. So 7 plus, 8 plus, hold on, my brain is not braining today. 18 plus 8 is 26. So there's 26 electrons. Put the Br in the middle and spread your O's out however you want, because that part is not particularly important. So I'll do it this way. Of my 26, I've so far used none, so let's bond them once. 1, 2, 3, 4, 5, 6. Whoops. Let me move this over here. All right, so I've used 6, which means I have 20 remaining. And spread them out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. If you look at your formal charges, it's negative, 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 plus 2. You don't really need the formal charges, but that's just something you might want to remember. Whoops. So that means the entire bromate ion has a -1 charge, as we saw. And as we saw earlier, again, that thing about knowing the geometries is really important, because we know that this central atom has 1, 2, 3, 4 electron regions around it. And when something has 4 electron regions, it's just sp3. Just recognize that. Hopefully that helps with the test.